Hey everyone, I want to show you an example where we're going to find the derivative of a function, but we're going to use logarithmic differentiation because it's going to make it go quicker. So if you want to differentiate this function without what I'm about to show you, notice that you would need the quotient rule and the product rule. And I think, yeah, and actually the chain rule as well. But we're going to avoid all that by using logs. So what you can do is you can actually take the log of both sides of the function. And I'm just choosing log base e, so natural log. And so what that's going to allow me to do is use my log rules that I've learned in the past to rewrite my function so that I can differentiate it actually much quicker. So the first thing I'm just doing right here is I'm going to rewrite this radical of square root as a 1/2 power so that we can in fact use our power rule. And so then I'm going to go ahead and use all my log rules. So we have a product rule for logs that says if I have the log of a product, I can separate that with the plus sign. I have a quotient rule for logs that says if I have the log of a quotient, I can separate with a minus sign. And then I actually have a power rule for logs that says I can bring this power down to the front with multiplication. So let's do all three of those at once. So we're going to use the product rule. So it's going to be ln of x squared plus 1 and then plus ln of x plus 3 to the 1/2 power. And we're going to bring that power down in just a second. And then from the quotient rule, minus ln of x minus 1. And so again, that's using our log rules. So now let me go ahead and use the power rule from logs. And I'm going to take this power right here, and I'm going to bring it down to the front with multiplication. So let's go ahead and erase that from here, and then move it into the front right there. So we have the plus 1/2 power going there, and we took it off right there. All right. Now what we get to do, because we rewrote this, we don't have to use our quotient and product and all those rules for differentiation. We can just take the derivative of each term here. So now if I differentiate this entire function, let's change colors real quick. So I'm going to take the derivative of the left side of this equation and the derivative of the right side here. And so then what we get is the derivative of each term. And so I'm going to account for the fact that I put logs into this problem that were never there. I'll do that at the end. So we have derivative of natural log is 1 over the argument of the natural log. But don't forget your chain rule. So times the derivative of the argument. So times derivative of x squared plus 1, which is 2x. And that's our derivative of this term. Then plus the 1/2 that was in front times the derivative of natural log, 1 over x, or of x plus 3, which the derivative of ln x plus 3 is 1 over x plus 3, technically times the derivative of x plus 3, but that's just an invisible 1. You don't really have to write that, but I'll put that there. And then minus the derivative of ln x minus 1, which is 1 over x minus 1. And then technically chain rule times the derivative of x minus 1. Okay, and this is pretty much it for the right side. We can kind of make this look a tiny bit better. We'll just say 2x over x squared plus 1. Right here, we can distribute the 2, and we can say plus 1 over 2x plus 6. And in the back, we'll just leave that. We could find a common denominator if you want and put this all together. We're going to go ahead and leave that. So this was the derivative of ln of our function y. So now we have to account for that. So on the left side here, we have to take the derivative of ln y, and so that's just 1 over y. Now, technically though, because y is a function of x, we have to say times y prime, or times dy dx. And so either way you want to write it, I'm going to go ahead and say the prime notation. So times y prime. So that's from, if you think about when we learned implicit differentiation, we have to account for y in terms of x. So that's why we needed this extra piece right here for the chain rule. Again, you can call that dy dx if you'd rather use that notation. So now your answer here, you're asked to find the derivative of y. So this is your answer as soon as you solve for it. So notice what you have to do. You have to solve for this derivative of y with respect to x. So what I'm going to do is I'm going to times both sides of this equation by y. And then that will be my answer. And then I have to rewrite this in terms of y, and I'll show you what I mean. So y prime, or if you want to call that dy dx, is the whole right side times y. So I'm going to rewrite the right side real quick. 2x over x squared plus 1 plus 1 over 2x plus 6 minus 1 over x minus 1 times y. However, I don't want to write this in terms of y if I can rewrite it. And I can rewrite it if you go back to the beginning here. We know what y is. We know that y is this whole thing right here. So I'm going to take this, and where I'm timesing by y in my final answer, I'm going to substitute what y equals into my final answer. So instead of saying times y, I'm going to say times what y is equal to, which was x squared plus 1 times square root of x plus 3 all over x minus 1. And this I can say is my final answer. Okay, so that's it. That's our example for using logarithmic differentiation.